Welcome to the Astrum Discovery Network, where we journey to the very edge of human understanding and explore the universe's secrets. In late 1999, humanity witnessed a catastrophic failure when a $100 million spacecraft vanished into the silence of space. The Mars Climate Orbiter disintegrated in the Martian atmosphere, not because of complex engineering failures, but due to a simple math error. One team used imperial units while the other used metric, causing a fatal communication breakdown that destroyed years of hard work. This disaster highlights a fundamental truth about our reality. To understand the universe, we must agree on how to measure it. But human measurements like meters and seconds are arbitrary, based on historical accidents rather than the fundamental laws of the cosmos. Enter Max Planck, the father of quantum mechanics, who proposed a system of natural units derived solely from universal physical constants. He combined the speed of light, the gravitational constant, and the quantum constant to create a measurement system for the universe. These are known as the Planck Units, representing the absolute limits of measurement, where our current laws of physics remain valid. To understand why these units matter, we must travel back in time, rewinding the cosmic clock to the very beginning. As we go back billions of years, galaxies merge into clouds of gas, and the vast cosmos shrinks into a point. We arrive at the Big Bang, a moment of infinite density and heat, where all matter and energy were compressed together. But as we approach the very first instant, specifically 10 to the power of negative 43 seconds, we hit a wall. This specific moment is the Planck time, the smallest possible unit of time that has any physical meaning in our universe. Here lies the great conflict of modern physics, a battle between Albert Einstein's general relativity and the rules of quantum mechanics. General relativity describes gravity and the large-scale structure of the universe as a smooth, continuous fabric of space and time. Quantum mechanics, however, governs the subatomic world, where particles exist in clouds of probability and nothing is ever truly smooth. Usually, these two theories work perfectly in their own separate domains, never needing to interact or cross paths with each other. But in the Planck era, the entire universe was compressed into a space smaller than an atom, forcing them to collide. At this scale, the universe was both incredibly massive and incredibly small, requiring both gravity and quantum mechanics to work together. This is where our mathematics breaks down completely, producing answers that are infinite or nonsensical, leaving physicists in the dark. To understand the scale, consider the Planck length, which is about 1.6 times 10 to the negative 35 meters. If you magnified an atom to be the size of the entire observable universe, the Planck length would be a tree. Below this length, the very concepts of geometry and distance cease to exist as we know them in our reality. It is theoretically impossible to measure anything smaller, as the energy required would create a black hole, destroying the information. Any attempt to probe deeper into the fabric of reality at this scale results in the creation of miniature black holes. Similarly, the Planck time is the time it takes for light to travel exactly 1 unit of the Planck length. Within intervals shorter than this, time itself loses its meaning, and the sequence of cause and effect becomes completely undefined. Physicists call this the search for quantum gravity, the holy grail that could unite the laws of the large and small. Finding a theory of quantum gravity is essential to unlocking the secrets of the Planck era and the universe's origin. One leading candidate is string theory, which proposes that all particles are actually tiny vibrating strings existing in multiple dimensions. String theory suggests that at the Planck scale, we would find 6 or 7 extra dimensions, curled up and hidden. If this theory is correct, the fundamental building blocks of reality are not points, but tiny loops of vibrating cosmic energy. Another contender is loop quantum gravity, which envisions space itself as being constructed from a network of discrete quantum loops. In this view, space is not a smooth background, but is made of individual chunks, much like pixels on a screen. Physicist John Wheeler proposed a radical idea called quantum foam to describe the chaotic nature of space at the Planck scale. Imagine the ocean. From high above, it looks smooth, but up close, it is a turbulent mess of crashing waves. Wheeler suggested that at the Planck scale, space-time is a boiling soup where geometry fluctuates violently and topology changes constantly. Microscopic wormholes and virtual black holes may be popping in and out of existence, defying our conventional understanding of stability. In this quantum foam, the smooth laws of Einstein's gravity are completely replaced by a storm of quantum uncertainty and chaos. After the Planck era ended, the universe expanded rapidly, smoothing out these quantum fluctuations to create the cosmos we see today. We can still see the fingerprints of these primordial quantum fluctuations imprinted on the cosmic microwave background radiation across the sky. Scientists are currently looking for subtle signals that might confirm which theory of quantum gravity correctly describes the Planck era. Advanced computer simulations are helping us peer into this opaque era, testing our theories against the limits of mathematical logic. The Planck era represents the ultimate horizon of our past, a curtain that currently hides the moment of creation from us. It forces us to ask profound questions. What exactly happened at time zero? And was there anything before the Big Bang? Until we can merge gravity and quantum mechanics, the first fraction of a second of our history will remain a mystery. As the universe cooled past the Planck temperature, the forces of nature separated, and the first distinct particles began to form. Gravity was likely the first force to break away, leaving the other forces unified in a state of grand symmetry. This cooling process allowed the laws of physics as we know them to crystallize from the chaos of the beginning. Just as the Mars orbiter failure taught us the value of precision, the Planck Units teach us the limits of reality. They remind us that our human-made measurements are just tools, while the universe operates on a much deeper, fundamental logic. Today, scientists use Planck units to effectively communicate across borders, and even potentially with extraterrestrial civilizations in the future. Because these units are derived from the universe itself, any intelligent species would eventually discover and understand these same constants. Max Planck's insight was not just mathematical, it was a philosophical leap that connected the observer to the fabric of reality. We are part of this universe, made of the same quantum foam and subject to the same gravitational laws he described. Some physicists even speculate that the Planck area represents the pixel size of our reality, suggesting a holographic universe. The holographic principle suggests that all information in our 3D world is stored on a 2D surface at the Planck scale. This idea stems from black hole thermodynamics, hinting that the Planck length defines the maximum density of information possible. As we build powerful quantum computers, we're beginning to harness the strange properties that rule the Planck scale world. These machines exploit superposition and entanglement, phenomena that become dominant as we approach the fundamental limits of the Planck scale. Perhaps artificial intelligence will one day help us find the mathematical bridge to cross the barrier of the Planck era. Moving forward from the Planck era, the universe entered the inflationary epoch, expanding faster than the speed of light itself. This rapid expansion took the microscopic quantum fluctuations and stretched them across the cosmos, creating the seeds of galaxies. Without those tiny irregularities from the Planck scale, our universe would be a boring, uniform soup with no stars. It is a poetic thought. The largest structures in the universe owe their existence to the smallest chaos of the beginning. The connection between the microscopic and the macroscopic is the key theme that runs through the story of our universe. Great minds like Stephen Hawking dedicated their lives to understanding how black holes connect to the physics of the Big Bang. Hawking showed that black holes are not truly black, but emit radiation, a quantum effect happening at the event horizon. This discovery was a crucial step towards linking gravity and thermodynamics, bringing us closer to understanding the Planck scale physics. Experiments like LIGO detect gravitational waves, ripples in space-time that give us a new way to listen to the universe. These waves carry information from catastrophic events, potentially offering clues about the conditions of extreme gravity and quantum limits. The James Webb Space Telescope allows us to look back closer to the beginning than ever before, revealing early galaxies. While it cannot see the Planck Era directly, it helps constrain our models of how the universe evolved from that state. The dream of a grand unified theory drives thousands of physicists to push the boundaries of mathematics and experimental science daily. Neutrinos, ghost-like particles that rarely interact with matter, might carry messages from the very first seconds of the universe. Facilities buried deep in the Antarctic ice are hunting for these high-energy particles to decode the history of the cosmos. The Planck mass is roughly equal to the mass of a flea egg, which seems large for a quantum unit. However, compressing that much mass into a Planck volume would create a singularity, making it a significant upper limit. The Planck temperature is the highest possible temperature, where particle energy becomes so high that known physics creates a black hole. At this temperature, the wavelength of light emitted would be the Planck length, making it the absolute ceiling of heat. As the universe cooled from this peak, it underwent phase transitions, similar to steam condensing into water, creating structure. Some theories suggest our universe might be just one bubble in a vast, foaming multiverse of eternal cosmic inflation. If the multiverse theory is true, each bubble could have its own unique physics and different values for Planck units. In another universe, gravity might be stronger or weaker, leading to completely different forms of matter and potential life. But in our universe, the Planck units are precisely tuned to allow for the existence of atoms, stars, and life. This creates the fine-tuning problem. Why are the fundamental constants exactly what they are, allowing us to be here today? Is it just a cosmic roll of the dice? Or is there a deeper underlying reason for these specific numbers? M-theory, an extension of string theory, attempts to answer this by unifying all 5 versions of string theory together. Some models suggest the Big Bang was caused by the collision of 2 higher-dimensional membranes, resetting the cosmic cycle. The Big Bounce theory proposes that our Big Bang was just the result of a previous universe collapsing and rebounding. If true, the Planck Era is not the beginning of time, but a bridge connecting a past universe to ours. Today, dark energy is pushing the universe apart, and understanding its nature might require solving the vacuum energy puzzle. The calculated energy of the quantum vacuum is vastly larger than what we observe, a discrepancy famously called the worst prediction. This mismatch of 120 orders of magnitude suggests we are missing something crucial about the Planck scale. Empty space is not truly empty. It is alive with fluctuating fields that contain immense amounts of potential energy. We can prove this energy exists through the Casimir effect. where quantum fluctuations push two metal plates together in a vacuum. Understanding these forces isn't just theory. It could revolutionize nanotechnology and how we manipulate matter at the atomic level. New discoveries, like time crystals, show matter behaving in ways that break time translation symmetry, opening new doors in physics. By cooling atoms to near absolute zero, we create states of matter that mimic the quantum coherence of the early universe. In a Bose-Einstein condensate, atoms lose their individuality and act as a single giant quantum wave, visible to the eye. This allows us to study quantum mechanics on a macroscopic scale, bridging the gap between the small and the large. We believe that at the Planck energy scale, all forces of nature were unified into a single, elegant superforce. As the universe cooled, this symmetry broke, shattering the superforce into the four distinct forces we experience today. The Higgs field froze into place later, giving particles mass, but the Planck era predates even the concept of mass. In the Planck era, it is possible that mass itself didn't exist, and everything moved at the speed of light. For a photon, time does not pass. If everything moved at light speed, did time even flow in the beginning? The emergence of time's arrow is one of the deepest mysteries, likely tied to the entropy conditions at the Big Bang. The universe started in a state of extremely low entropy, highly ordered, which is statistically incredibly unlikely to happen by chance. Boltzmann gave us the tools to understand this order, but the initial order of the Planck era remains a baffling puzzle. Roger Penrose suggests that the end of one universe, when all mass decays, becomes mathematically identical to the Big Bang. This conformal geometry trick implies that the infinite future of one aeon is the Planck scale singularity of the next. Penrose claims we might see concentric circles in the cosmic background radiation, scars left by black holes from a previous aeon. While controversial, these ideas show how the Planck era forces us to rethink the boundaries of beginning and end. Let us dive back into the quantum foam. Imagine a landscape where up, down, left, and right lose their meaning. In this foam, space is not a stage for events to happen. Space is the event itself, constantly changing shape. The Heisenberg uncertainty principle states that we cannot know both position and momentum perfectly, creating a fuzziness in nature. At the Planck scale, this uncertainty allows energy to be borrowed from nothing, creating particles that exist for fleeting moments. If enough energy is borrowed, it creates a virtual black hole, which immediately evaporates, adding to the foam's turbulence. This suggests that reality is discrete, like sand grains, rather than continuous, like water, a fundamental shift in perspective. It echoes the ancient paradox of Zeno, asking if space can be divided infinitely, or if there is a smallest step. Planck Units answer Zeno, there is a smallest step. Motion is actually a series of tiny, instantaneous teleports. If we could see at the Planck scale, smooth motion would look like a character moving on a low-resolution computer screen. Mathematics creates new geometries, called non-commutative geometry, to describe this strange pixelated fabric of space-time. Mathematicians like Alain Connes are building the tools to map this territory, treating space as a spectrum of frequencies. It brings us back to the idea of music, the universe as a symphony of vibrations playing on the strings of reality. The deep connection between abstract mathematics and the physical world is nowhere more evident than in the Planck units. This is what Eugene Wigner called the unreasonable effectiveness of mathematics in the natural sciences. It is the only universal language. A civilization a billion light years away will agree on the value of the Planck length, while our empires and languages will fade. These constants are woven into the eternal fabric of the cosmos itself. The center of a black hole is another place where the Planck Era conditions exist right now, hidden from our view. Inside the horizon, space falls faster than light, and time directs you inevitably towards the singularity. Loop quantum gravity suggests the singularity is not infinite, but a Planck star, a core of maximum density. Here, quantum pressure prevents collapse to infinity, potentially allowing the matter to bounce back out eventually. This could mean black holes eventually become white holes, spewing their contents out into the future or another universe. Because of extreme time dilation, this bounce might take billions of years to happen from our outside perspective. Some theorists even propose that our entire universe exists inside the event horizon of a gigantic black hole. The math of the Big Bang looks suspiciously similar to the math of a black hole forming in a higher dimension. This leads to a dizzying concept of nesting dolls, universes within universes, all born from the physics of the Planck scale. Lee Smolin proposed cosmological natural selection. Universes that produce more black holes create more baby universes. This would explain why our constants are fine-tuned for stars, because stars create black holes, the reproductive mechanism. In this view, life is just an accidental byproduct of a universe optimized for creating black holes. Regardless of the theory, the quest to understand the Planck era is the quest to understand our origins. We have come a long way from measuring with our feet and hands to measuring the vibrations of atoms. Science teaches us humility. The more we learn, the more we realize how much is hidden in the Planck scale. The Planck wall still stands, guarding the secrets of the first instant, challenging us to break through. It will likely be a curious mind from a future generation who finally cracks the code of quantum gravity. Perhaps the answer will be a simple equation, one that you could print on a t-shirt, uniting all forces. When we find it, the veil will lift, and we will see the birth of the universe in clear detail. From a crashed Mars orbiter to the edges of space-time, the lesson is the same. Precision matters. Max Planck gave us the map. It is up to us to build a ship that can sail these waters. These numbers are the coordinates of reality, the bedrock upon which the entire cathedral of physics is built. As we stare into the void, we don't just see darkness, we see the potential for infinite discovery. If you enjoyed this deep dive into the smaller scales of the universe, please like and subscribe for more. We have many more journeys planned, from the edge of the universe to the center of the atom. This has been a production of the Astrum Discovery Network. Thank you for watching and keeping your curiosity alive. Until next time, keep looking up at the stars and wondering about the secrets they hold within. Stay tuned for a brief look at how we visualize the impossible physics of the Planck era in this video. Creating the quantum foam required simulating millions of particles to represent the chaotic fluctuations of space-time. Visualizing the unseeable is a challenge, bridging the gap between abstract mathematics and human imagination. Our team of artists work closely with physics consultants to ensure these representations are as accurate as possible. The shapes of extra dimensions are mathematically precise, based on the equations of string theory geometry. Special thanks to our channel members and supporters who make these high-quality educational documentaries possible for everyone. As Einstein said, the most incomprehensible thing about the world is that it is comprehensible. We hope this video helped make the incomprehensible Planck era a little more comprehensible to you today. From the macro scale of our home planet, we are poised to explore the deepest mysteries of nature. Remember, the GPS in your phone relies on both relativity and quantum clocks, using physics from this story. Without understanding these fundamental laws, our modern world and technology would simply cease to function correctly. One day, mastering the Planck scale might allow us to manipulate gravity and travel to the stars. Warp drives and wormholes are currently science fiction, but they are solutions allowed by the math of gravity. The journey that began with measuring a king's foot may lead us to footsteps on other worlds. Every measurement we make is a step outward, extending the reach of human knowledge into the dark. The structure of the universe and the structure of our brains share a remarkable similarity in their complexity. It is this curiosity that drives us to ask, how small is small, and how did it begin? We stand on the shoulders of giants, adding our own small measurements to the great library of science. And somewhere, a child watching this might be the one to solve the puzzle of the Planck Era. The dance of the quantum world continues, silently shaping everything around us, every second of every day. In the silence of the void, the laws of physics are the only sound, whispering the truth of reality. Let us continue to chase that light, pushing back the boundaries of ignorance, one Planck length at a time. Astrum Discovery Network is dedicated to bringing you the highest quality science content on the web. Don't forget to subscribe and hit the bell icon so you never miss a discovery from our universe. Check out these other videos exploring the mysteries of time, black holes, and the nature of reality. While we explore the stars, we never forget the incredible beauty and complexity of our own planet Earth. It is the platform from which we launch our imagination into the deepest reaches of the cosmos. Like Voyager, we are travelers, carrying the message of humanity into the vast unknown of space and time. Our measurements and mathematics are our universal language, encoded in the very structure of the spacecraft we build. Those signals are now traveling past nearby stars, carrying our understanding of physics to whoever might be listening. If they hear us, they will know that we understand the Planck Units, the common ground of intelligence. Knowledge is the force that binds the universe together, creating meaning out of the chaos of the quantum foam. The lights may dim in the lab, but the search for truth never sleeps, continuing in minds everywhere. We keep the candle of curiosity burning, illuminating the dark corners of the Planck Era and beyond. Even when the flame goes out, the smoke rises to join the stars, just as we will.